afternoon. Any questions before I get going? So someone asked me by email if I could go over this homework assignment. So let's do that real quick. So in part 1, we needed to add on a couple of features. We needed to add on a definition. So a definition binds a name to an expression. And then we wanted to be able to evaluate an expression given a bunch of those definitions. So that's this program here. So a prog has a list of definitions and the expression in which it should be evaluated. So in the parser, we need to parse the definition. So I have a val def for that. And so that's a val, an ident, an equals, an expression, and a semicolon. And then I want to transform that into a def. So here, I think the grammar rule is straightforward enough, right? If you didn't have these arrow things here, then it would be totally clear. A val, ident, equal, expr, and a semicolon, just 5 things squiggled up. And then one gets ambitious and wants to get rid of these various tokens, and so that's where the arrows come in. So we want to drop the val, we want to drop the equal, we want to drop the semicolon because they don't add anything. And then you have to, you put on the arrows pointing to the things that you retain, and then one has to struggle a little bit with parentheses because now the less than squiggle has the wrong precedence. So I've put the parentheses around here because I happen to know from another situation that I had, like from the expression parser, that this part works. It throws away the left and the right and just leaves me the identifier. Then back here, I don't really have to worry about parentheses because as long as nothing comes after the less than squiggle, then I'm fine. If it's the last thing, that always works. So now what's left over is just 2 things squiggled together, the ident and the expr, and then I use a case statement here and make my def. So that's hopefully fairly straightforward. But I must say, I did see when people sent me some code that had trouble, I did see some amount of things that weren't possibly going to work here, and it always had to do with parentheses. Someone asked in the previous section, can I just, if I find this a hassle with the parentheses, can I instead leave the val and the equal and the semicolon in place and add them to the case statement? Then it would be a case val squiggle s squiggle equals squiggle e squiggle semicolon. And yes, you can absolutely do that if you find it simpler. And there's no penalty for it. Like in the exam, I'm not going to complain and say that whether this is more or less elegant. As long as it works, I'm fine. It's not our job here to come up with the most elegant grammar. Anything that works is okay. So pick your poison. Either you throw away tokens and use parentheses, that makes your case simpler, or you keep all of the tokens and don't have to worry about parentheses, but then you have to schlep them into the case. So the prog is, again, pretty simple. It's a rep of the val defs followed by a single expression. And then again, I need to build up my element. And in this case, I don't have to do anything because the val def rep gives me a list of them. So someone asked in the preceding section, what's rep? So if for whatever reason you haven't seen what rep is really your friend, right? It is the simplest way of collecting a sequence of things of the same type. And you get them just back as a list, and then you just work with it. So here's the expr, we don't need a transform either, we need an expression. So another thing that I'd like to just point out is that when you look at one of these things, you should always be aware what prog and valdef and expr and so on, what they actually are. What are they? What is prog? What is valdef? What's expr?
Expr is an expression.
They're functions. They're all functions, okay? They're all Scala functions. They're things that are called, okay? And the reason I say that's useful is because it helps you really understanding what a parser does. This thing here, if you look at this one here, this quote val quote is actually converted to a function. And if you look carefully, there's like a little underline here, and the underline means that there's what's called an implicit conversion that turns the string into a function. That is the function that eats the string val. If it eats val, it's happy and returns val. If it finds any other string, then it just throws an exception. So the squiggle means you first call the first function and then the second function. So we've called the val function that eats up the val. Then we call up the function called ident. Ident returns the identifier. Then we call another string parser. And then we call this function that whatever does. This is this function here. It returns an expression. Okay? So each of these are functions. Over here, let's see what rep is. Rep is a function that takes a function. What rep does, it keeps calling this function for as long as it can. So at some point, of course, valdef is going to throw up and say it didn't work anymore, and then rep stops and says, okay, that was one too much. And then, so that's what rep does. It keeps calling this function. And then the expr function is called. All right, so that's one of the things for the parser. Now that takes care of the parser, so there was 2 lines of parsing that had to be added onto this thing. Maybe 3, because down here you have to modify the ident, to add the ident to the factor, right? Ident has to return a variable. Now all of this was part of a lab, but depending on how far you got in those labs, so it's possible that all of these 3 lines were brand new lines that you needed to add. Now the other part now is then to evaluate this thing. So to evaluate, you need to implement this eval function here because all of the expressions here have an eval function. We've already given the eval function for numbers and for operators, but for variables, again, depending on how far you went with that lab, to evaluate a variable, you need to look it up in the symbol table. To evaluate a number, of course, it evaluates to itself. And an operator, it's like what we had before, except when you compute the left and the right, they're expressions, and they both need a symbol table to do the evaluation in. Now the only hard part is how do we evaluate a program. We have a bunch of definitions and an expression, and so now we need to evaluate the expression with the correct symbol table. How do we get the symbol table? So you start with the empty symbol table, you then process the first definition, and then you get a better symbol table. You process the second definition and you get a better symbol table, and so on. So over here, because this was the structure from one of the labs, I used this function eval_def that takes an existing symbol table and a single definition and makes a better symbol table out of that by taking the existing symbol table and then adding the binding of the name and the value. I'll come to this thing in just a second. And now I need to repeat that process with all of the definitions, and that's what the fold over here does. So anytime that you need to do something for lots of different things, see if you can do it with a fold one step at a time. And the one step at a time in this case is actually this eval_def function that encapsulates one step. So one recipe for writing folds, which are always a little bit challenging, is if you find that it's confusing to write a fold where you have to worry about the seed thing and the fringe list and then some anonymous function, you can always give that function a name. And try to say, what does it do in plain English, and give it that name. See, I call it to evaluate a definition. Now, there was one slightly confusing aspect maybe, and that is the symbol table maps strings to integers, to the values that the symbols have. But that's not what you're getting in a definition. A definition has a name and an expression. So So someone in the preceding section said, oh, hey, I'm just going to change this int to expression. I wasn't here. So if you do that, he got the program to work, and it worked with basic cases, but at one point he got in trouble. What way do you think that strategy would get you in trouble? If you keep the expression unevaluated in the symbol table. He did have to evaluate it later, of course.
When the value of one of the variables in one of the expressions.
That's right. So if you have an x equals 1, say, and then you have y equals x plus 1, and then you say x equals 2, then it makes a difference whether you evaluate it early or late. And so, do I have something like this on the board? Satisfied. So, if you have this SL1 program, x equals 1, y equals x plus 1, x equals 2, and then we evaluate x plus y, then I think when most people read this, they would say, well, this means y equals 2, and so the whole answer should be 4, right? And so that is in fact the interpretation that we're after. And so that's where it makes a difference. So let's see how it's done here. So here we're evaluating the expression right away when we put the thing into the symbol table. And as it happens, whenever you evaluate, you have to say with what symbols. And this works quite nicely, the symbol table that we already have, the one that has all of the old definitions in it. All right, so that's all I can think of with the first one. But the various bits and pieces that are in here that are useful and that you should internalize are, certainly how to do this kind of basic parsing, how this evaluation of a single definition works, and then how you put the entire symbol table together with this fold. Now, Part 2 and Part 3 were really basic exercises in parsing. And so, well, actually, in the interest of capturing this on the video, let me try to do this with the homework description. Where is it? Here. That's homework 7. So we have these lists, and they can have a bunch of numbers followed by colons. And then in the end, you have to have either a list, or you have to have the word nil, right? Where do we have those? Or not? What did I say anything about nil in here?
I don't know. I didn't do any nil.
You didn't do any nil. So in that case, then one would have to at some point end up with an empty list.
I had a nil just to make sure.
You had nil just to make sure. Now I'm wondering about my test cases. Did anyone look at my test cases yet, whether they contain a nil?
I have not.
I don't remember. Okay, we'll find that out in a minute when we look at them. In that case, I would have to change the test cases before the grader gets a hold of them. So the way that it's spec'd out, there was no mention of nil, and so this thing would then have to have a list which might be empty.
Professor, did you include test cases in your zip file?
I think so. Oh, you know what? I may not have. Send me an email about that, because then the poor grader doesn't have them either. Because he has the same zip file that you have.
Yeah,
I must have forgotten to zip them up, because I remember it's always tedious to zip this thing up since there's all this guff in there that we don't want. Yeah, or put it on Piazza and I'll fix it.
I'll mail you.
Yeah. No, either way, I'll fix it in a few minutes. Okay, so now we have to come up with some kind of a grammar. So let me just get some piece of scratch area here. So we'll have to say a list is, and so we have a number, we have a colon, And we could say we have some repetition of those, if that's the scheme I'm using. Or not, we can just recursively say followed by a list. Or we can say it is a parenthesis followed by numbers followed by parenthesis. And then numbers is a sequence of numbers that I have to somehow write up. So in BNF I would then say numbers is it's nothing or a number, comma, whatever. But I'm not even going to bother with this because in Scala I can use repsep for that. Anytime that you have a comma separated something or a space separated something or whatever, then you use repsep. Repsep is really your friend because it takes care of this nastiness. What if it's empty, that you have one less comma than the things. So you definitely want to, if for whatever reason you're not familiar with repsep, have a look at that. So repsep takes the individual function that's being called and the separator, and then it gives you a list of the results of calling the individual functions. All right, and so now once I have that, things aren't too hard because if I have a whole number followed by a colon followed by another list, the recursive call, then I just convert the number to an integer because it's a string, and I cons it with the recursive list. In the other case, I have a list of numbers, and that's really easy because when I have a list of numbers, it's already itself with one little wrinkle. It's not really a list of numbers. What does this thing here, what does repsep of whole number return?
A list of whole numbers, can be 0 or any sign.
Right, but what's in the list?
Whatever type whole number is.
Whatever the type whole number is, let's find out what it is by mouse over it, and it says it's a parser of string.
The template of the parser type, so string.
Yes, so I'm getting a list of strings. Okay, each call to repsep gives me a string. They're all put together into a list of strings. Now that's a little bit unfortunate because I want to have a list of int, but if I have a list of strings and I just want to transform each of them into an int, that's what map is for. And so that's what I'm doing here. I'm taking my list of strings and I'm mapping so that each of the elements is an int. So whenever you have a list of values and you need to do something with it, you kind of need to ask yourself, what do I use, map or reduce or fold? That's kind of always your first go-to thing. If you can do one of those, then that's good. Otherwise, you have to start writing a custom recursion, which takes an extra 5 minutes or more, and so you don't really want to do that. So in this case here, I have strings, and I want to turn them into integers. That's a clear case for map. And so if map works, I always go for that. Fold is always more complicated than map. I'm sure I could set this up as a fold, but that would really be not as easy to understand. So map is, in this case, will grip. And that's all you need to do.
I think it's a good idea to have like an intermediate parser, like a parser of ints that equals the whole number converted to an int.
Now that's a good question, and so let's try that out. So I'll call it element, and that would be a parser of int. And so that would be would take a whole number and transform it to an int. In that case, over here, I could call element, and then I wouldn't have to do any transform here, because what I'm getting back is already a list of integers. Okay, that's a neat trick, right? So this way we're saying we don't want to deal with those strings. We whip them into shape right when we have them in our hands, and then later we don't have to work as hard in this case.
I also found that there's a repsep 1 and a rep 1 that can be useful for this, where it has to be at least 1 instead of 0 to...
Right, that is true, except in my case I do want to allow the empty list.
Wait,
I have to be able to allow the empty list because otherwise, I want to be able to say 1::2 empty list. Particularly since I did not define a nil.
Oh yeah, but I have, it's either that or a standalone element,
Yeah.
where I find standalone to be like nil or something like that.
Yeah, there's many ways of doing it, yes. And so in the context of a homework or an exam, in this class we're not really worried about what is the best way of doing it. If you have a way that works and you're satisfied with it, that's fine. I'm not going to say, you must change it. Sometimes I might say, you could do this better and avoid backtracking, and sure, listen to this, but you don't have to go back and change anything. It's not a compiler construction class. Okay, so that's kind of two different ways of slicing that, and I'll just leave this. I don't really have any preference. The third one is the XML elements. So you have an identifier for the start tag and then for the end tag, and they have to match, or you have one of these self-matching ones like you have in HTML, and then you can have name value pairs of attributes in them, and that's all you can do. The big challenge, the grammar by itself is not super challenging, I don't think. So you start out with a less than symbol. You have an identifier. You then have a sequence of attributes. And here I guess I'm using what you were using. I say, I don't want to think about what an attribute is right now. I'll just call another function to capture an attribute, even though it's pretty trivial to do that. And then I have, and at this point I ran into this situation that I said, gosh, now life is getting a little complicated because there's two possible cases. I could have the closing bracket and then the child elements and then the other thing, or I could have just the closing element. And I said, I'm just going to have a separate rule for that because it's getting too much because that's crammed into one rule. It also has the advantage that this way I don't have to worry about any backtracking. That it might not be a big deal, but I felt that was the simpler way to do this. And so then I said, okay, I have these two possible cases for the tail. And then I had a bit of a technical problem that the tail is a function. It delivers some result back to element so that element can assemble the final element. And there's two possible cases. One is that tail has found out that it was a self-closing element, or tail has found out that it was a child elements and a closing tag. So there are these two cases, and I've had to figure out how do I transport the information across from tail to element. Now, it's a function that returns something. It's up to me what it returns. And in Scala, a common thing that you do is when you have some random agglomeration of stuff that you need to transport from place A to place B, you say it's not really worth making a new class for it because you only need it once. You just put it in a tuple. So here I said, what do I need to carry across? I need to carry across the child elements, and I need to carry across the identifier of the end tag. So the child elements, that's a list. So I say, fine, that's a list. So I'm saying I have a pair where the first thing is a list of children. And then I have that end tag, but I don't have an end tag if I have the slash angle bracket. And I said, well, if I sometimes have a tag and sometimes I don't have a tag, the Scala way of doing it is to use some or none, to use an option. And so that's what I did. I said, I'll return the list of children, which might be empty if there are not any, and I'll return the end tag, if there is one, as an option. So let's see how I did that. In the first case, I said, okay, that was just the end tag. What do I return? I have an empty list, and I don't have an end tag. So that's the nil and the none. In the other case, I do have a list, which the rep gives me just like that, and I have the end tag identifier, so I put them together in the pair. This is my list, and this is the identifier wrapped in a sum. Now, when I receive this in the element, I now have two cases, right? This identifier and the attribute list always give me an identifier and an attribute list, but the tail can give me one of two cases. I could have a pair with a matching end tag, or I could have a pair where there is no, where there are no children. And so I then treat both of these cases separately. Here's the case where I have the identifier of the end tag wrapped in a sum, and then I use my guard, this if I equal j statement, so that it only matches when that is the case. So, and that's here where the partial match operator came in that I described in the assignment. For some reason, when I did this match, I had to put, this is the pair, and then I had to put another set of parentheses around it. When I didn't do that, I got some crazy error message. I never quite understood why that was the case, and maybe I will someday. But so that's why I warned you. Now, some of you will have come up with a completely different strategy for this, right? You may have just stuck all of this stuff here where I have tail right into expr, and that's perfectly fine. Then, of course, your match rules will get to be slightly different, and you have to adjust for that. And just to show a second way of doing it, no, maybe actually the way that I did it is a little funky. Maybe I should have said that in the case of that there's really two logical cases. There's the case of no children and no end tag, and then there's the cases of children and an end tag. So instead of having a pair of a list and an option, maybe I should have an option here of a list and a string. Maybe that would be a little cleaner. Let's do it. I need to put my pair syntax here. It's an option, angle bracket, and then here another angle bracket. That way, in this case, I just say none. And in the other case, I would say sum of c comma I. Yes?
Are we supposed to call the thing list instead of elements?
Yeah.
Because I botched it up real fast.
I get it.
The parser element is supposed to be called list.
The
Yeah, so it
The
does.
method element should be renamed to list as per the instructions of your homework.
Oh, I see. So this parser was misnamed.
Yeah. It's supposed to be called list.
I didn't even know why I called it element. Okay, can we fix that later?
Yeah.
Let me first of all do this, and then I hear what you're saying. Yes. For the XML, it was supposed to be called list.
Yeah. I think you probably just copied it.
Okay, I think I'll leave it as element, and I'll fix the homework assignment. The good thing is I never call your program. I just run it, and so as long as you have it consistent in your program, it doesn't matter. Yeah, but that would have been a good thing for someone to point out on Piazza and say, why the heck is it called list? Okay, back to this. So now I've changed what tail returns, and then this tail here now returns my new thing, and so then all of this stuff here needs to be adjusted as well. So I would put a sum of Cj here, and then I would just put a none here. And now let's see. And then here the C has become an empty list because there aren't any. And here I have a parentheses. Oh, I need a pair. It's a sum of a pair. And now it should be good. So maybe that's more elegant. you can ponder that. Right now that I look at it, it seems more elegant to me. All right, so those are my solutions to the homework. Now there was a very large amount of unhappiness about this particular homework, that it was really hard and everything. So let's reflect a little bit about what's hard about these things.
Well, for me,
Yeah.
my suggestion to you, like for homeworks, would be just add more test cases and explain more about edge cases.
Okay,
Let's say for part 2, I didn't even think about the empty list or
okay,
these kind of things. Yeah, I would just assume it's just a number or column.
okay,
Or next
okay,
one.
that's interesting.
I swear that's the only thing for me.
Okay, so with these edge cases, that's a very good comment, right? And so where I'm trying to get people to is that, as you write these things, that you think about these, and if you're not sure, ask on Piazza.
It's extra time.
It does, yes. I'll come back to that in a minute. So what other things are like hard and confusing about this?
Like, for me personally, I have no idea what the hell all these symbols and classes are. But I know how to kind of like piece them together, but like I don't know like why it actually works.
Okay, and that I think is where, if you ask yourself a little bit more, how this thing actually, what it does. So knowing that each of these is a function that gets called, I think is kind of helpful. So if you think about what happens here, we're calling the function that eats up the less than. We're calling the function that produces the identifier from the remaining input. We're now repeatedly calling the adder function. And whatever the adder function is produced is then bundled up in a list. And then we're calling the tail function. That is what this thing means. The squiggle means and then. The squiggle with the arrow is just a little trick that says, and then, don't tell me about the left part. If you think about this, the squiggle means and then I think I hope it makes some sense to say, call a function that eats some input, call a function that eats some input. Repeatedly call a function that eats some input, call a function that eats some input. And that really is what happens. It keeps calling those functions. That's what the parser does. Now, then there's the issue of what's the vertical bar mean? What that means, it first tries to call, and so really all of this thing here is then again wrapped up into a function. That's maybe a technical thing, but so when you write this, the compiler produces a function call that makes this combined function. But that's not something we normally have to think about too much, except in the situation with the vertical bar, because the vertical bar means try to call the first function. If it succeeds, great. If not, call the second function. And what does it mean if it doesn't succeed? Then that means if the parse doesn't match at some point, then it gets unrolled. And then whatever input was consumed to try to make the match gets put back. So that's the two things. Squiggle means call the first function and then the next function. The vertical bar means call one function, and if it succeeds, keep on going. If not, call the other function. So that's what those symbols mean. And so immediately that is confusing. So now what about these funky hat symbols? Those mean, of course, that when that function has returned, it gives you a chance of transforming the value into something more convenient. And so I think I like the example that you guys had here, where you said, we're going to simplify what element does. We didn't like what element returned. We're going to put the transform in here. And so that basic trick of saying, if you find it's too messy, that this is all interleaved, one could certainly try to break it down into further parts, right? Although I guess this one is not all that messy. No, I think this one is fine. We don't have a lot of branches here anymore. Yeah, but so from understanding it, having this as a sequence of function calls, hopefully will demystify somewhat what the parser does. So for me, the biggest problem is always with the syntax errors. That with these pesky arrows, you don't put the parentheses right. Like, for example, let me omit these parentheses. And now I get a syntax error that says, Yeah, and so at this point, I say I might as well shoot myself, because I will never figure out, what all of these 19 markers mean. And now, as it happens, the correct error message is somewhere in here. It's the one with the constructor that cannot be instantiated. But maybe that is hard to do. It's particularly in the exam, where you probably do not have the time to go through this entire long list. In this case, you simply have to know that the thing with the squiggly arrows is a persistent sign of trouble. It's something that's very easy to get wrong. And then you just, put in parentheses. I could put a parenthesis around here, because I know from experience that having a delimiter, an identifier, and another delimiter, with the squiggles that point to the identifier, that work. Because I've also seen it with expressions, left parenthesis, expression, right parenthesis. So then that'll surely work. And then I have another one here, and I'm just going to put parentheses around this, because that should also work. That way I throw away this thing and I'm left with the other thing. And in that case, now my error has gone away. It's probably a slightly different set of parentheses than I had before. So that's fine. The other thing is, sometimes you don't actually have to put in the return type when you have something that's not recursive, but it might actually be a good idea to put it anyway. Like over here, let's look at what adder does. It returns this pair here. And you can actually see that it does that, because it is a parser that gives you a pair string, string. But it's not a bad idea when you get confused to put it in, and explicitly, it's a parser that returns what? Okay, it's a pair of strings, and the way you write that in Scala is like this.
String though and job tokens parser.
Yes, and I did give that as a hint. And someone complained and said that he didn't pass one of my test cases, which means he must have gotten them somehow, because that person used a quoted string and then an ident and another quoted string.
Yeah, that's what I did.
Yeah, and
Include your test cases, by the way.
what's that?
You did include.
I did them. Okay, that's good. That's how I then knew. Okay, and I didn't think about that. I said it's a string, right? Anything could go in that string, and I happened to have a string that said UTF-8, and that's not a valid identifier because you can't have a dash in it.
Yeah.
You'll lose a point in it. That's okay. There's some professors that when they give a homework assignment, they expect everyone in class to get 100% to get an A. I don't do that. I mean, I'd rather have you learn from some of the mistakes that you make. So as long as you get a good number of the things right, then it's fine.
What's a good number, in your opinion?
Typically, it's like 80-90% or so. That's plenty for an A or even an A+. But if you get 30%, that's not so good. And then we'll have to figure out what to do about it. Yeah, but I mean, if you have like the occasional slip up, so as you can tell from my slides, I slip up all the time, and so I'm not one to penalize you for a minor little thing. All right, now how do we test this stuff? How do we run these test cases? Let me demo that really quick. I'm going to show it right now. We're gonna, okay, come on. We're going to unzip my assignment, go into it, and so it does have all of the test cases in it. It has the rubric in there. See what's in the rubric. The rubric says to run these things, and there's 2 points per test case. So the grader doesn't have to do too much here. So how do we run one of these test cases? It says right here. so here the answer is 1729. And let's see what that test case was. Part 1 in 1. And it's at x is 12 and x cubed plus 1. That looks like. Okay? So to do that with your solution, so what you would do with your solution is you would leave my solution intact, except you would replace the 3 Scala files with your 3 Scala files. And then you can already anticipate exactly what the grader would do. If you already see that runs you into trouble, you could let me know, or you could wait until the grader has done their thing. But at any rate, you can now see what would be happening in the grading. Any questions about any of this?
Sorry, were you able to run everything at once? All commands?
No.
So
I don't know of any SBT way of running everything at once. So what I told the grader is to just make a shell script that contains these 12 statements. And depending on how clever he is, he could filter out the things that start with info and warn, so he doesn't have to look at them. You could collect all the answers into one file. I'll leave that to his creativity. If I was grading my own thing, that's what I would be doing. I would just make it so that there's only one line for each output, and then I would put them all in a single file, and then diff them with my expected answer.
Create a script that runs it, gets everyone's repositories updates and then
I have a script that updates everyone's repository, because I need to do that several times a week.
you just run one script and grade that.
That's what I normally do, and that's what I encourage him to do. Some graders catch on to this faster than others. Any final questions on this? Okay. The other thing that I did want to say is that when I need to do one of these things, and then I run into one of those compiler messages from hell, what is the single most helpful thing in that case? So when you see the compiler message from hell, what is the greatest help? To me, the greatest help is if I'm not in a hurry. If I'm not in a hurry and I'm relaxed, I look at the thing, I can see the answer right away. But if I have to get it done in 15 minutes because then I have to go to the lecture or because the homework has to be posted, then I'm really stressed out, and then I see 9 error messages, and then I get a mental block. And so if you are the same way, the only way that you're going to make headway with these more complex scenarios is to start early. Just tell yourself the thing is due Saturday night. And then you have some extra time in reserve. I actually do the exact same thing when making the programs for the labs. I don't do them the day before they do, because I tried that once and I almost had a heart attack when it didn't work out. And so now I always do it a week or two in advance. And then it goes super smoothly, because when you're relaxed, you say, okay, it didn't work, I'll try another thing. Then it's not usually that big a deal. But I personally find it very stressful to get an unfriendly error message when I'm under pressure. So know yourself and know how to pace yourself. I think that really is useful advice. And this is all new stuff. Like the rest of your life is going to be. Almost everything that's worthwhile doing is going to be new and uncomfortable and different. And so you just have to be able to get a grip on that. All right. That's that. Let's get a very brief word on homework 7. Since I said, we should start early. So homework 7 starts out simple. You're writing an SL1 function to let you write a somewhat non-trivial SL1 function. And then you're going to make 2 changes to the SL1 interpreter. Each of those changes is, I think, less than 5 lines of code. But of course the trick is where in those 130 some lines of code in SL1 should they go. The first one has to do with, by sheer mistake, I forgot to make it so that one can parse multiple function invocations. So the current SL1 parser cannot parse things like f of x of y, which can happen, right? F of x could return a function, and then you'd have to be able to call of y on it. And it's a simple mistake. When you find out where the parsing happens, you're probably going to see right away what the mistake is. and you're hopefully going to see right away what you need to fix the parsing, there's a little bit of a thing that you have to do then to fix the evaluation. Because right now, you're going to see it's going to evaluate f of, with a single argument list, and now you're going to have a list of argument lists, and then you have to figure out how to deal with it. So, sorry, let's see, 3 lines of SL1 need to be changed. Then the other thing that I'm asking you to do is to make it so that SL1 can parse lists. In this case, we do have nil, but we don't have the list notation. So it's actually easier than in homework 6. All you have to worry is colon, colon, and nil. And the parsing itself is fairly simple. You return a Scala list from the parser, in this case. The only messy part is to do evaluation, because when you evaluate the colon, colon, then what you get in out of eval is an any, and this one also gives you an any. And in order to make that work, you have to do a cast, and I'm showing you how to do that here. To actually make use of the lists, we need to have some list primitives, and so we need to have the functions head, tail, and is empty defined. There's no way of defining them in any great way other than just implementing them. And so what you will do is you will preload the symbol table with the definitions of these 3 things. And while we're at it, you'll also preload them with the definition of nil that you can use. So that means when one of these things comes out, then they kind of parse, then you evaluate them to themselves. So I'm describing how to do that, and the description is about 5 times as long as the code that's involved in doing it, as so often in Scala. Then after all of this, then there's this bonus feature with the Y Combinator. If you don't have the time to look at it, don't look at it. It's entirely optional. But it's interesting that it works, and so I will talk a little bit about it at some point. But yeah, if you have extra time, it's definitely a fun feature of this assignment that you can do this, because you would be able to say in a job interview, hey, I've written a language that does recursion using the Y Combinator. And if you interview for the Y Combinator startups, then that'll definitely get you to the next round of interviews. That's what I want you to explore. So I can tell you, but if I know this from experience, if I tell you, your eyes will glaze over and you will only remember one thing, that the Y Combinator is hard. But if you discover it yourself, then you will remember one thing, namely that it's cool. So I want you to discover it yourself. But there's no obligation. You don't want it, you don't have to do it. All right, moving on with the short lecture here. So, this lecture deals with variable scope, this mini lecture really. And so when you have some entity that has a name, such as a variable name or a function name or a class name, then these names have meanings in some areas of the program, and they might not have that meaning elsewhere. So here I'm defining a variable foo. And over here in this function fun, when I'm using foo, that's exactly the integer foo that you see up here. Over here, I'm also having a variable foo, but it now refers to a different variable, right, to the one over here. You know that's like that in Java and C++ and so on. So we say that the scope of a identifier is the region in the program where that identifier is visible and is bound to what you think it's bound to. So the scope of this local variable is everything from this from the opening brace to the closing brace of the function called fun. Of this function called fun. The scope of the integer foo, because it's an instance variable of the class, is the entire class, except of course where it's shadowed by this other one. Now there's some programming languages where you're not allowed to have more than one identifier with in a program. So for example, in the C language, you would not be allowed to have 2 functions with the same name and different parameters. Those languages don't allow overloading. There are some very primitive languages where you're not even allowed to have two variables with the same name anywhere in the program text. The second one you would be flagged as illegal. In fact, a little bit of that is true in Java. In Java, when you have a local variable in a method, and then say you have a for loop, and inside the body of the loop, you want to have another local variable of the same name as one that's defined outside, that's illegal in Java. Java says that you cannot have two local variables of the same name inside a method. I don't know if it happens to me once in a while that I forget that rule in a longer method, and then I just have to rename. Yeah.
Java can't have a this dot for a global variable.
Well, that's a little different. You can have a parameter variable and a instance variable with the same name, and then you can disambiguate with a this dot trick. But what I'm saying is, suppose that inside here I now make an if statement or a for loop, and inside the body of the if or a for, I try to define an int foo or another double foo. That would be illegal because there's already a local variable called foo. So the Java designers, for some reason, chose to make this extra rule that's wrong. that disallowed that. I don't even know what it is in Scala, but my guess is Scala does not make a special rule like that, because it seems a bit against the spirit of that anything should go anywhere that Scala has. And in C and C++, of course, there's no such rule either. You can define a local variable really anyway. But it's not a good idea to disallow too many of these nested variables. It's because really we want to be able to just define variables with abandon without having to think about what might already be defined in an outer scope. And so in Scala, of course, I can define a variable x here. It doesn't matter at all what goes on in an outer scope at all. This just defines me a new x. Now, so that's the notion of a scope. That's the area of the program where a variable has a particular definition. Now, there are there's a couple of technical definitions here that you also want to know what is the value of a variable. And if the value is determined solely from the program text, one calls that static scoping. There's another situation where the value of a variable could depend on the program execution history, and that's called dynamic scoping. It's easiest to explain with an example. In this example, I start out defining x as 1. I then define f of y as x plus 1. In static scoping, at this point here, it is absolutely clear what f of y is. It's a function that adds 1 to y. Because you can read from the program text that at this point, x is 1, and so this must be 1, and therefore this must be the function that adds 1 to y. In dynamic scoping, that's not true. In dynamic scoping, we say the meaning of this depends on whatever x was when we reach this function call. So in my example here, I'm defining f, I'm defining g. Now I'm calling g in the definition of g, x is set to 2, and now I'm calling f, and in this case here x is 2, so when calling f, this x is 2, so it adds 2 to its argument, so the answer in this case would be 4. Now you might say, why would anyone want to do a silly thing like that? It seems like really complicated to say that the meaning depends on what x currently is. But there's some number of programming languages that do that because it's easy to implement. And so
that wouldn't compile in Scala, would it? If you have a val definition of x and then you have another val definition of x.
Oh, this would compile just fine. Why wouldn't it?
Because you define val x is equal to 2, and then the x reference is ambiguous whether you're referencing the.
Well, let's just try it.
I'll use the most inner
Well, because if you try to say val x and then val x again. I don't think it works.
Follows a rule like using the most inner thing, then I guess it works. But I think
It's like some button for sure.
Yeah, why am I getting an error here? Okay, let's just do it one at a time here. So we say, oh, because I didn't put types in here. Okay, now I'm going to have to rewrite it. Say val x equals 1. That'll work. Def f of y colon int equals x plus y. That'll work. Def g val x equals 2 f of x works.
That's weird because if you try val x is equal to 1 and do something, then val x is equal to 2, then it doesn't.
Okay, okay, now it doesn't return anything. Why does this one return unit? Oh, because I didn't put an equal, because I'm a knucklehead. Okay, I need to put... Okay, now it returns an int. So first of all, it returns 3, so it means it's statically typed. Now back to Tyler's comment here. This x here has nothing to do with the x over here. It's a different x. It's only in this scope.
If you didn't put val x is equal to 2, would you still be able to access the x in the outer scope? You would be, right?
Yeah, so if I omitted this thing here,
It would just be...
then this x would be that x. But they're different. Since I did define it, it's a new x that shadows the original.
yeah, I think it's allowed in C++, but it's not a good idea. Compiles, they give you warnings about it.
No, I don't think so. I mean, that happens all the time. You have a global variable, you have a local variable with the same name because you don't always know what you have in the outer scope. You will not get a warning in C++, I'm quite sure.
I think you do, because all the compilers are like prefix, like other functions with like double underscores to make sure.
Well, if you want to have a unique name, I mean, you may need to do that because otherwise someone could have come up with the same bright idea. But I'm quite sure that in C++, if you translate this to C++, it will work without a warning. Okay, so on to dynamic scoping. So dynamic scoping is easy to implement. The way you do it is as follows. You keep a symbol table, and you push in definitions into the symbol table. So over here, I would say, okay, x is 1, and I push the mapping from x to 1 in here. Then I omitted the mappings for f and g here, but now so when I execute in here, I come into the definition of, into the body of g, and in the body of g, now x is set to 2. That gets pushed in front. Now we're getting to the call of f here. Y is now defined as the value of the argument, which is 2. And these definitions, x is 2 and x is 1, persist. And now when we evaluate x and y, we look up the leftmost definition, and both x and y are bound to 2. So it's a simple way of implementing this by just doing the kind of table that you've seen actually in the lecture last time. Yes?
So how would that go about if you want to access the first instance of X?
Well, you couldn't because it's hidden. I mean, the fact that one value is shadowed by the other, that's a fact of life in all programming languages. And so here the dynamic scoping rule says that if you have now temporarily set x equal to 2, that is the value that x has, literally. That's what dynamic scoping means. And no, you can't get to the other value. Just like in the situation on the previous slide here, if you looked at this here, a Scala here, when I'm inside here, I can't get at this x if I want to or not. Yeah?
Isn't the difference just like reading the table left to right or right to left?
Well, the way I've written this here is that the table is written left to right.
But like if you read it right to left, it would be static.
No, we'll come to that. So the one thing that I didn't put on the slide is when G exits, it needs to pop off the definition of F exit. F needs to pop off the definition of Y bound to 2, and when G exit, it pops up the definition of X. So that's kind of a normal stack-based symbol table that whenever a new scope is entered, you push the new definitions. Whenever the scope is exited, you pop them up. And that way the symbol table always reflects the dynamic history of what the variable bindings should be. Now let's see how we would implement static scoping. So, and let's just look at this example again. Here we're having x is 1, and then now we're defining f of y as x plus y. So my intent in static scoping is, of course, that when f is called, that x is 1. So what I could do is I could rewrite the right-hand side and rip out all the x's and put in 1's. But as you can imagine, that could get tedious. What if x was defined as something really complicated, and it occurred several times? And that kind of editing of expressions doesn't sound like a fun thing to do. But here's a trick on how you can avoid the rewriting of the expression. What you do is you store together with f, not just the body, but you also store like a mini symbol table that says what all of the free variables are. So in this case, we have one free variable, that would be x, and y is the parameter. And so if we store a symbol table that says, when you evaluate this body, make sure that x is 1, then you just evaluate it in the normal way. So here we're going to say that a function is not just the body of the function, but it's the body of the function plus that symbol table, plus the assignments of all of the free variables. Yeah?
So it's like a program, it's like a closure, right?
That is what a closure is. So a closure is a piece of code plus some indication of which ones are parameters and which of the free, what are the values of the free variables. So that's what you need to do to do static typing. Whenever you have a function, you need to put that scoping information with the function. And then this way, when we're now calling f of x, let's see what happens. We have a symbol table in which x is 2, and now f is called, and two new symbols are now established, namely x to 1 from the closure table and y is 2 from the function call, from the parameter. So one needs to establish those two bindings, and in that augmented symbol table, then we evaluate x plus 1. But it's important that you store that information together with f, what x is here. So that is the trick on how to implement closures. Now, the SL1 interpreter does exactly that. So whenever it captures a function, then it also keeps a record of what the bindings of all the variables are at this time, and it stores that together with it. So let me show you that real quick. So here we have a class closure that has the params, that's just a list of strings, the names of the parameters, the body, that's the block, and then over here I have the list of string comma any pairs, that's my symbol table. So that's what a closure is. It's a function, except together with this list of bindings. So with that, and let's actually look at what a function called is.
Does that mean you can look at a whole prog as like a closure, but with no parameters?
Yeah, and that's really what it is, because when you evaluate the entire thing, let's see where we have that, we are evaluating a block with the empty list, that's our no bindings going in. Oh, by the way, hint for homework 7, in the third part where you put in the definitions of nil and is empty and head and tail, this is where they go. That way you start out your program with what these four things are instead of with nothing. Now, over here is how a closure gets evaluated. So the closure has params, a body, and the symbols that come in. We're evaluating the function arguments that come in from the call, that's the args here, and then we're prepending that to the symbols that we already have. And that's the binding in which we do the evaluation. That's all. So at some point we need to capture a closure. Let's see where we do that. That's in the parser. And I see. So that happens when we have a definition of a function. Then the eval def thing actually only produces the closure. And then there's another case where we do that, and that's the one that I want to show on the slide. So there is a problem with the closure idea when you have recursive functions. So as a reminder, recursive functions are a special case. You could normally define any old functions by just using val, except if the functions are recursive. So look at an attempt to define a recursive factorial. This is the Scala code here. So we would say, if x is 0, that's 1, otherwise it's x times factorial of x minus 1. This definition will not succeed because the scope of the right-hand side does not yet have a binding for fac. So in this expression here, fac is a free variable, and it's just not going to work. It's in Scala, the compiler would say, I don't know what fac is. If we did the same thing in SL1 and we evaluate the thing, then in the evaluation fac would not be bound to anything. So we of course use a def for this, and that's the reason to use a def is to do something extra so that fac is defined in terms of itself. That we say, when I mean fac, I mean the function that I'm just in the process of defining. And so we need somehow to make the simultaneous definition. Here's the code from the SL1 parser, where if we evaluate a def as opposed to evaluating a val, then what am I getting? I am getting a name, and I'm getting something that is a function. A function is the thing that parses the right-hand side, has params and body. And now I want to turn this one into a closure. So a closure has the params and the body, and it has the symbol table. Now which symbols? There's some symbols that are already coming in from the outside world, and I need to grab those. And if this was not a recursive function, if this wasn't a def, I would be done at this point. That would be my closure. That I would simply remember the symbols that were in force when this thing was evaluated. But now I need to add one more symbol, namely I need to say the name that this function has, in my case fac, is bound to the exact same closure, to the one that I've just defined, to this triple here. And so I now augment my symbols, and as I add this binding to it, and now I need to take the closure env part, which is these symbols, and modify it to add the new symbol onto it. Now normally you wouldn't be able to do this in Scala because closure.env is this thing, it's these symbols, and I can't add anything onto it. You can't do mutation. And so that's where this red var comes in. I've made it so that this field is actually mutable. So this is the one and only one time in this entire course where you will see me use mutation. And it's very strange that in order to implement recursion, you need mutation. So we are doing all this functional programming, right, where we say we're pure. We don't have any mutation. We write everything with recursion because we wouldn't be able to do any loops. Loops are useless when you can't mutate. But in order to actually implement recursion, you need mutation.
Or you could implement recursion with recursion, right?
Well, and so, there's actually some wisdom to what you say. So if you want to implement recursion in a kind of normal and straightforward way, then you have the situation that the recursive definition lives in an environment where, like if you look at fab, right, where this fab must be the thing that you are in the process of defining. So then you have this technical problem. What comes in is an environment that doesn't contain fact, but you need to put in the fact that doesn't yet exist while you're defining it. And there's any number of ways you can arrange it, but all of them require a mutation one way or another. You can push that mutation to different places, but that's just the way it is. All right, so and so the question is, of course, is there some other way? And so there is a way where you can define recursion without mutation, and it uses what's called the Y Combinator. And I'm not talking about the Y Combinator in this class because it is it's an advanced concept. But so if you do have the extra time after you're done with homework 7, I invite you to have a look at that little article about the Y Combinator, about how it's. Now I'm giving you a couple of files where you can see it in action. And it is a truly marvelous thing that it works. But it is complex and it's not super practical. But from a practical perspective, this is how one would implement recursion.
Like object in Java, anything?
Yeah, any is like object.
And you can, okay. And so when you do the dot NV, that's like a dereference, right? You're setting the actual.
Yeah, I mean you've seen it like this, where it said I just want to have the end field.
Yeah, but that's like a.
But by declare it as a var, you can have it on the left-hand side.
Yeah, but that's not like a local, like struct like in C. It's like Java where, that's like a dereference, right?
It's like a struct in C. I mean, it's the same thing. There's no difference between a struct in C and an object in Java.
Or in C, like if you can have like structs by value, right?
Oh, I see.
That's like the.
I see. No, so in that regard, sure. In Java, everything is a reference. Everything is a pointer.
In Java, it's like the arrow operator.
Yes. Okay. So yes. But what this simply means is that your env is a field, and then you're setting that field of disclosure to symbols again. And the thing is, the way it's uncomfortable is you first make the closure with symbols, because you have to make it with something. You can't construct it with nothing. And then you mutated symbols, so to speak, because you added something in there. So another way you could implement it is by having this list here to be a immutable data structure. Now you could use a mutable map or some such thing, or an array buffer or something. But somewhere you have to put in some mutation. Yeah.
So if we use Y Combinator, will we get any significant increase in performance for now?
Oh, it'll be slow as molasses. Yes. Yes, it's completely impractical. And you can see that, and I've actually done that for fun by when you read your SL1 interpreter by putting in some print statements. If you put in a print statement or a SPI statement at every expression evaluation, and then you see how the factorial works with the Y Combinator, and I give you the code for it, you don't have to figure it out. Then, yeah, you can see that it makes like a huge number of calls. And it's totally amazing that it computes the right answer, if you ask me. All right, I guess the time is pretty much up. I just wanted to show you what's in the lab that we didn't do. But it's a pretty simple lab that you can do. So I'm introducing good old Bash, the programming language that's used for the Bash shell. It is not a great programming language, as you can see by just looking at some code here. So here's a Bash program. We're setting x to the string 2. We're having a function that just prints something. It does that with the echo command. In Bash, when you want to look up the value of a variable, you can't just write the variable. Because, what if you just could? You have to put a $sign in front of it, and that means the value of the variable, whatever. Here we're having another function. In Bash, when you want to make a local variable, you have to put the word local in front. Undoubtedly, because there was an older version of Bash where they didn't even have local variables, and then they added it in later. So then the question is, what does this program print? Does it print 2 or does it print 3? What do you think? So here x is set to 2. F clearly says, print whatever x is, which is 2. But here we're setting x to 3, and then we're calling it.
Depends on static or dynamic.
Yeah, so it depends on whether bash is dynamically scoped or statically scoped. And so when you run this, you can try that, just put it in a file and run it in a bash shell, it'll print 3. And so bash is an example of a dynamically scoped language where over here it sets 3 in that symbol table, it then calls f, then when it calls f it looks things up in the symbol table. It has no memory of the environment in which f was defined, but only a memory of what happened when the program ran. So bash is dynamically scoped. So why is bash dynamically scoped? These days no one, I think, would come up with a new language that is, but bash is pretty old, and at the time maybe the guy who wrote it didn't know about static scoping, or maybe it's always too complicated to implement, or who knows. So nowadays people understand the value of static scoping and will do it, but it is what it is. So every once in a while you run into one of these languages that has this difference semantics, and then you can say, oh, that's because it's dynamically scoped. All right, that's all.